Hello everyone, and welcome back to Tech Adventure. Hope you're doing great and staying sharp in your journey of software development, embedded systems, and interview preparation. In previous videos, we covered ADCs, RTOS, top 50 real-world C and C++ interview questions, solid principles, common design patterns, and other key interview Q&A. If you missed those, be sure to check them out. They lay a solid foundation for what's coming next. Today, we'll explore one of the most popular communication protocols in microcontrollers and learn how it's used for interfacing. And exploring key hardware blocks, real-world applications, and common interview questions. In today's video, we dive into the SPI, Serial Peripheral Interface, protocol, its basics, modes, signal lines, configuration, and popular interview questions, with clear explanations and practical examples. Let's dive in.
Welcome to the Deep Dive, the show that's basically your shortcut to getting genuinely well-informed. We turn dense info into stuff you can actually use and hopefully give you a few aha moments along the way. Today we're diving right into the heart of digital communication. We're talking about SPI, the Serial Peripheral Interface. It's buzzing away inside pretty much everything, from tiny sensors in your watch to, complex industrial robots.
It really is everywhere. SPI, it's a synchronous communication protocol. It's specifically designed to connect microcontrollers to other digital bits and pieces, think sensors, displays, memory chips. It's like having a dedicated high-speed hotline for data. Super fast, incredibly reliable data transfers. That's why it's key in so many electronic systems.
Right. So in this deep dive, we're going to peel back the layers. We'll look at exactly what SPI is, how it works, which is quite clever, actually, why it's become such a standard, a workhorse in embedded systems. And crucially, we'll get into practical insights, the challenges, the triumphs you'll face using it in the real world. Get ready to sort of see the invisible forces at play in your tech. Okay, so let's kick things off right at the beginning. What is SDI exactly? And why is it just so fundamental for anyone working with embedded systems?
Okay, so FPI stands for Serial Peripheral Interface. And like the name says, it sends data serially. That just means bit by bit, one after the other, over specific wires. It started as a point-to-point thing, one master controller talking directly to one or more peripherals. Why it's so big and embedded? It really boils down to how directly and efficiently a microcontroller can chat with these other specialized chips using it.
And when you dig into the why it's everywhere, a few big advantages jump out, don't they? First, it's fast, like really fast data transfer, often way faster than other common protocols, maybe like I²C or UART for a lot of common jobs. Second, it's full duplex. That means it can send and receive data at the exact same time. Third, the hardware side is pretty simple, usually just 4 basic signal lines we need to worry about. And finally, it gives you really precise control over the data flow, which is absolutely critical for things where timing is everything, like, say, fast displays or those analog to digital converters.
Yeah, those 4 lines are key. You've got MOSI, that's master out, slave in. That's the line the master uses to send data to the slave, the peripheral. Then there's MISO, master in, slave out. That's for getting data back from the slave. SCLK is the serial clock. Think of it as the conductor, keeping everything synchronized. And finally, SS or CS slave select or chip select. This one's important. Each peripheral gets its own unique CS line. It's how the master picks which one device it wants to talk to out of maybe several connected. So you have one master, potentially many slaves, and each slave is managed by its own CS line. That's a really core strength.
Okay, so I'm picturing this sort of communication dance now. The master picks a slave, pulls its CS line low, wakes it up, basically. Then it starts sending out those clock pulses on SCLK like a heartbeat. And with each pulse, a bit goes out from the master on SI to the slave. And at the very same instant, the slave can send a bit back to the master on MISO. It's like a perfectly timed two-way street.
Exactly. And you find SPI doing this kind of workhorse job in loads of places you might not even think about. Cameras, for sure. Those crisp displays on smart devices. Flash memory chips, like storing photos on an SD card, or the firmware in your smart plug. RF modules for wireless stuff. ADCs and DACs converting signals. Loads of sensors, motion, environmental. Even real-time clocks use it to keep accurate time.
So looking at the big picture then, SPI's big pros are speed, simplicity, that full duplex thing, and it's relatively easy to get going with it. But like anything, there are trade-offs, right? It usually needs more wires than something like I²C.
Yeah.
There's no built-in error checking in the hardware itself. It's really only good for short distances, and it doesn't have that standard addressing system like I²C. But even with those points, it's often the go-to, the express lane, when speed and direct control are what you really need. That makes a lot of sense, especially the express lane idea. But how does SPI really fit into the bigger picture? You mentioned I²C and UART. How does it stack up against those common siblings?
Yeah, that's a really important comparison because they each have their sweet spots. Let's break it down. Wiring. SPI typically needs 4 wires, like we said, MOSI, MISO, SCLK, and that separate CS for each slave. I²C and UART, they get by with just 2. SDA and SCL for I²C, TX, and RX for UART, so fewer pins needed there.
Okay, wire count is one difference. What about how they talk?
Right, communication type. SPI is full duplex, send and receive simultaneously. I²C is half duplex. Devices have to take turns talking or listening. UART is actually full duplex too, like SPI.
When speed, you said SPI is fast.
Generally, yeah. Speed. SPI is usually the speed demon, often tens of megahertz, sometimes even higher. I²C is more moderate, usually up to maybe 1 megahertz, maybe 3.4 in fast mode plus. UART is typically the slowest. Its speed is limited by the baud rate setting.
Okay. What about hardware complexity? SPI needs more wires. Does that make it more complex?
It's interesting. Hardware simplicity. SPI needs more pins, yeah, but its directness can make interfacing quite straightforward. I²C uses fewer wires, and its addressing scheme makes connecting lots of devices easier on just 2 wires. UART is probably the simplest in hardware, often just 2 direct connections needed.
In connecting multiple devices.
Multiple devices. SPI handles 1 master talking to many slaves, but remember, each slave needs its own CS line, so it can get pin-intensive. I²C is really good for having multiple masters and multiple slaves all on the same 2 wires, using addresses to pick who talks. UART is mainly point-to-point. 1 master, 1 slave, typically.
Gotcha. And synchronous versus asynchronous.
Right. Protocol type. SPI and I²C are synchronous. They need that shared clock signal, SCLK or SCL. UART is asynchronous. No shared clock. It relies on start-stop bits and agreed-upon timing the baud rate.
What about distance? You mentioned SPI is short range.
Yeah, distance support is generally short for all 3, honestly.
Oh,
but SPI, especially when you push the speed, is the most sensitive to wire length, gets noisy fast.
And error checking.
Error checking. SPI has basically none built in at the hardware level. You have to add it in software if you need it. I²C has a basic AC connection acknowledgement mechanism. UART can have an optional parity bit for very basic error detection.
Okay, last one. How complex are they to implement in software?
Implementation complexity. SPI is, I'd say, moderate. Pretty straightforward commands. I²C can be a bit trickier because you have to manage the addressing, the start-stop conditions, and the AC kind of signaling. UART is usually quite simple, often just setting up the serial port and writing bytes, to make it maybe a bit more memorable. Think of SPI like shouting really fast between friends using walkie-talkies. It's quick, direct, private channel for each friend. I²C, that's more like a controlled group chat. Everyone has an address. Messages are maybe a bit slower. You need acknowledgments to keep order. And UART is like sending a direct text message between just 2 people. Simple, but maybe slower, and timing matters so the message gets through correctly.
That walkie-talkie analogy really works. It paints a clear picture. Okay, so we know the technical differences, we have the analogies, but let's get really concrete. What are some hands-on, practical examples of how SPI is actually used in real embedded projects? Where does it shine?
Absolutely. Let's dive into some common uses where SPI is often the best choice. First up, connecting flash memory. Could be EEPROM or NOR flash. This is super common for storing stuff like device firmware, config settings, maybe sensor logs. So your microcontroller uses SPI to read and write to that flash chip quickly. The key insight here isn't just boot speed, but enabling things like real-time logging of complex data, or even over-the-air firmware updates, things that might be painfully slow with other protocols.
Right, so speed enables more complex features there.
Exactly.
Let's really zoom in on one. You mentioned connecting flash memory. Let's say we want to connect an external flash chip to maybe an STM32 microcontroller. How would you actually do that step by step in practical detail? Let's get into the deep part of the deep dive.
All right, let's roll up our sleeves. First things first. You got to pick the right chip. You're usually choosing between SPI, EEPROM, and SPI NOR flash. EEPROMs are often smaller, good for small, frequent updates like config settings, because you generally don't need to erase before writing. NOR flash gives you much bigger storage, but, and this is key, you typically have to erase a whole sector or block before you can write new data to it. So if you're storing firmware, big logs, images, NOR flash is probably your guy, but you have that erase step to manage.
Okay, so NOR flash for big stuff, EEPROM for small, frequent stuff. Got it. How do you wire it up?
Okay. Hardware connections, power, VCC, and ground, G&D, obviously. Then your 4 SPI lines, SCK, clock, MOSI, master out, MISO, master in, and your CS, chip select. CS connects to a regular GPIO pin on your microcontroller, one you can control in software. Now, some important reliability tips here. Any unused pins on the flash chip, like hold hashtag or WP tag, write protect, usually need to be tied HGH, often through a resistor, to your voltage supply so they don't float. Power needs to be clean. Always put a small decoupling capacitor, maybe 0.1 microfarad, right next to the chip's power pin, plus maybe a larger one, like 1 microfarad nearby for bulk capacitance. Signal integrity is huge, especially for the clock. A small series resistor, maybe 22 to 33 ohms, right on the SCK line near the master can help reduce ringing, especially on longer traces.
Okay, decoupling caps and maybe a series resistor on the clock.
Yeah. And if your microcontroller runs at, say, 5 volts and your flash is 3.3 volts, which is common, you absolutely must use level shifters between them. Otherwise, poof, you could damage something. And finally, a pull-up resistor, maybe 10K ohms, on the chip select line is a really good idea. It keeps the chip deselected during microcontroller boot up or resets, preventing accidental commands.
Right, those little details can save a lot of headaches. Okay, so it's wired up. How do you tell the microcontroller software what to do?
Good question. You need to configure the SPI peripheral on the microcontroller. If you're using something like an STM32, you might use their CubeMX tool, which is graphical, or write the code directly using their HAL library. You set the microcontroller's SPI unit to master mode. Set the data size, usually 8 bits. Then you need to set CPOL and CPHA clock polarity and phase. This is critical. Most SPI flash chips use mode 0, which means CPOL 0, CPHA 0. So the clock is idle low and data is captured on the first edge, the rising edge. You set your master to match this.
Mode 0. Got it. What else?
You'll usually set the chip select NSS pin to software mode. This means you'll control the CS pin manually using regular GPIO commands, pulling it low when you want to talk and high when you're done. Hardware NSS is less flexible for multiple devices. Data order is almost always MSB first, most significant bit first. And then you set the baud rate prescaler, which determines the clock speed. Start slow, maybe divide the system clock down to get 8 or 12 megahertz. You can try pushing it higher later if your setup is clean and the flash chip supports it. Oh, and make sure that GPIO pin you're using for chip select is configured as an output, set to push-pull, and its default state should be HIGH, inactive.
Okay, master mode 8-bit, mode 0, software CS, MSB first, conservative clock speed, CS pin set up right. Makes sense. Now, how do you actually talk to the chip? Do they have like a language?
They do. It's a command set defined in the chip's datasheet. You absolutely need that datasheet. For common NOR flash chips, you'll see commands like read ID to check you're talking to the right chip, write enable, you must send this before any write or erase operation, read or fast read to get data out, page program to write data, usually up to 256 bytes at a time, and various erase commands, sector erase, block erase, chip erase. You also need to understand the chip's status register. 2 bits are vital. YIP, write in progress. This bit tells you if the chip is busy doing an internal write or erase. And well write enable latch. This confirms that you successfully sent the write enable command.
Way enable well. Okay. And EEPROMs are similar.
Similar commands, but usually no separate erase step needed. You can often write byte by byte or page by page directly. You still need write enable, though, and they often use 16-bit addresses instead of 24-bit, like larger NOR flash.
Gotcha. Okay. Can you walk us through the actual step-by-step workflow? Like, how do I read some data? How do I program some data? How do I erase?
Sure. Let's take NOR flash as the example. To read data, first, pull the chip's CS line LOW. Then send the command byte for a read or fast read. Follow that with the 3-byte address where you want to start reading. If you used fast read, you usually need to send 1 extra dummy byte now just to give the flash time. After that, you just keep clocking the SCLK line, and for every 8 clocks, you read a byte of data coming back from the flash on the MISO line. Read as many bytes as you need. When you're done reading, pull the CS line HIGH to deselect the chip. Simple enough.
Okay, read seems straightforward. What about programming? You mentioned that's trickier.
Yeah, programming a page needs care. This is where things go wrong often. To program a page, say up to 256 bytes on NOR flash, first crucial step, the sector containing the page you want to write to must be erased first. If it's not already erased, all 0 IFFs, you need to perform a sector erase operation on that 4 KB sector before you try to program.
Okay. Erase before program.
Yes. Then you absolutely must send the write enable command. Just send that single byte. Then pull CSLOW. Now send the page program command byte, followed by the 3-byte starting address within the page. Then send your data bytes, up to 256 of them. Super important, make sure your data buffer doesn't cross a page boundary. A page is typically 256 bytes. If you try to write 300 bytes starting halfway through a page, it'll likely wrap around back to the beginning of that same page, overwriting what you just wrote. You have to manage this in your code, potentially breaking writes into multiple operations if they cross boundaries.
Okay, watch those page boundaries. What happens after sending the data?
After the last data byte is sent, pull CSHIGH, but you're not done. Now comes the critical part. You must pull the status register. Send the read status register command repeatedly. Check the WIP bit, write in progress. It will be 1 while the chip is busy internally writing the data from its buffer to the flash array. You keep checking it until it goes back to 0. Only then is the write operation truly complete.
Right, gotta wait for that WIP bit to clear. What about erasing?
To erase a sector, usually 4 KB on NOR flash, again, first send the write enable command, then pull CS low. Send the sector erase command byte, followed by the 3-byte address of any address within the sector you want to erase. Then pull CS IGH. And just like programming, you must pull the WIP bit in the status register until it goes back to 0 nut. Erasing takes time, often tens or even hundreds of milliseconds. Don't try to do anything else with the chip until WIP is clear.
Okay, erase also needs write enable and polling WIP. And EPROMs.
EPROMs are simpler here. Usually no separate erase step. You send write enable, then the write command, address, and data. Writes might still take some time internally, so checking already busy status or just waiting a specified time from the datasheet is often needed. And remember that page boundary wraparound thing still applies to EPROM page writes. Performance tips. Always use fast read. If available, it's significantly faster. For moving large blocks of data, definitely look into using DMA, direct memory access, on your microcontroller. It offloads the CPU completely, always respect those page boundaries, always pull WIP with a timeout in case the chip hangs. For critical data, maybe read it back after writing to verify it. And if you're writing constantly, think about where leveling algorithms. Oh, and for crazy speeds, some chips support QSPI or OSPI quad or octal SPI using 4 or 8 data lines, but that's a whole other level of complexity.
Wow, that's incredibly detailed. Super helpful. Okay, thinking about all those steps, what are the absolute most common pitfalls or, gotchas that trip people up when they're trying to get SPI flash working reliably with, say, an STM32?
Oh, there are definitely common ones. Number 1 is probably getting the CPOL CPHA settings wrong. Always double check the data sheet, usually mode 0, but verify. Number 2 is not respecting page boundaries during programming. Writing past the end of a page and having it wrap around unexpectedly corrupts data. Forgetting to send the right enable command before every single program or erase operation. It's easy to forget, and the chip just silently ignores your command. Not polling the WIP bit after a program or erase. Sending the next command while the chip is still busy internally. Recipe for disaster. You need that polling loop with a timeout.
Okay, those seem like big ones related to the commands and timing. What about hardware issues?
Absolutely. Signal integrity issues, especially at higher speeds. Long traces, noise, reflections, they can garble data. Keep traces short, use ground planes, maybe add those series resistors. Chip select glitches, especially during boot up. If CS floats low briefly, the chip might get activated unintentionally. That pull-up resistor on CS helps prevent this. Also, ensure your GPIO is initialized high before enabling the SPI peripheral. And a subtle one, mixing locking and DMA transfers without careful management of the chip select line. If you start a DMA transfer but your code accidentally toggles CS high before the DMA is finished, you'll terminate the transfer prematurely. CS needs to stay low for the entire duration of the DMA transaction. These are the kinds of bugs that can take days to track down if you're not aware of them.
That makes sense. Okay, let's shift gears slightly. You mentioned earlier that SPI is full duplex. How does it actually manage to send and receive data at the exact same time? That still sounds like a bit of magic.
It does sound cool, doesn't it? But it's actually quite elegant. Full duplex just means data can flow in both directions simultaneously. Think of it like two people on separate phone lines talking and listening at the same time. SPI achieves this because it has those two dedicated data lines we talked about. MOSI, master out, slave in, for the master send data, and MISO, master in, slave out, for the slave to send data back. During every single SPI clock cycle, while the master is putting a bit onto the MISO line, the slave is simultaneously putting a bit onto the MISO line. Both lines are active on every clock pulse.
So even if the master only cares about reading data.
Exactly. Even if the master's main goal is to read, say, 10 bytes from a sensor, it still has to send 10 bytes on MOSI. These might just be dummy bytes, like all zeros or all ones. It doesn't matter what they are. The act of sending those dummy bytes is what generates the necessary clock pulses on SCLK. And it's those clock pulses that tell the slave when to put its actual data bits onto the MISO line for the master to read. So the master sends a dummy byte on MOSI, generates 8 clock pulses, and during those same 8 pulses, it reads the meaningful byte coming back from the slave on MISO. It's this simultaneous bit-for-bit exchange that defines full duplex SPI.
Ah, okay. The master has to send something just to generate the clocks for the slave to respond. That clarifies it. This simultaneous thing must rely on super precise timing, right? What exactly are CPL and CPHA again, and why are they so critical for this timing?
You nailed it. Timing is absolutely everything. CPL and CPHA are the two configuration bits that define the exact timing relationship between the clock signal, SCLK, and the data bits on ONOW and MISO. CPL stands for clock polarity. It defines the idle state of the clock line when no data is being transferred. If CPL 0, the clock line is low W when idle. If CPL 1, the clock line is high GH when idle. Simple as that.
Okay, idle state, low or high. What about CPHA?
CPHA stands for clock phase. This one dictates when the data bits are actually sampled, read, relative to the clock edges. If CPHA is 0, data is sampled on the first clock edge of the cycle. If CPL 1, data is sampled on the second clock edge of the cycle. Now, what counts as the first or second edge depends on your CPL setting. If CPL 0, idle low, the first edge is the rising edge and the second is the falling edge. If CPL 1, idle high, it's the opposite. First edge is falling, second is rising.
Okay, so CPL sets the baseline. CPHA sets when to read relative to the clock transitions.
Exactly. And these two settings combine to give us the 4 possible SPI modes. Mode 0, CPOL 0, CPHA 0, idle low, sample on first rising edge. Mode 1, CPOL, CPA 0, CPHA 1, idle low, sample on second falling edge. Mode 2, CPOL 1, CPHA 1, idle high, sample on second rising edge. Why are they critical? Because if the master and slave don't agree on the exact same mode, they'll be sampling the data at the wrong time relative to the clock. Even if they're connected correctly and the clock is running, the data bits will be shifted or misinterpreted. It leads to complete garbage data.
Total garbage. So you have to get the mode right.
Absolutely. It's probably the single most common cause of SPI communication failure. You must check the slave device's datasheet, see which mode it requires. Again, mode 0 is super common for things like flash, ADCs, displays, and configure your master microcontroller's SPI peripheral to match perfectly.
Got it. Now, unlike some other protocols, you mentioned SPI doesn't really use start-stop bits or addresses in its basic form. So how does it frame the data? How do master and slave stay locked in sync without those markers?
That's another aspect of SPI's elegant simplicity. It doesn't need complex framing like UART start-stop bits or I²C's address bytes baked into the core protocol. SPI communication is essentially just a continuous stream of bytes. The structure or framing is imposed by the master at a higher level. Typically, a transaction consists of maybe one or more command bytes sent by the master, potentially followed by address bytes, if talking to memory, and then the actual data payload bytes being sent or received. The total number of bytes in this transaction, the length of the frame, is entirely determined by how long the master keeps the chip select line low and keeps generating clock pulses.
So the slave just still follows along.
Pretty much. The slave doesn't inherently know if it's receiving a command, an address, or data, or how long the total message will be. It just sees the clock pulsing while its CS line is low, and it shifts bits in on a MOSI and out on MISO according to the agreed-upon SPI mode, CPOL or CPHA. Synchronization is maintained purely by that shared SCLK signal generated by the master. Both devices use the clock edges, as defined by CPOL CPHA, to know precisely when to shift the next bit out and when to sample the incoming bit. The flow is just. CS goes low W. Clock starts pulsing. On the active clock edge, master puts a bit on MISO, slave reads it. Simultaneously, slave puts a bit on MISO, master reads it. This repeats bit by bit, byte by byte, until the master stops clocking and raises the CS line HEH. The slave just follows the master's rhythm.
Okay, that makes sense. The CS line going low and high defines the overall transaction boundary, and the clock keeps everything aligned bit by bit within that boundary. Now, you said one master, potentially multiple slaves. How does that work without them all trying to talk at once?
Yes, the multi-slave setup. This is where that dedicated chip select CS line for each slave becomes absolutely crucial. The architecture is one master controls the SCLK and OSI lines, which are shared by all the slaves. The MISO line is also shared, but, and this is the key, each slave device gets its own unique individual CS line connected back to a separate GPIO pin on the master.
Okay, separate CS pin for each slave.
Exactly. Think of it like a teacher, the master, in a classroom with several students, the slaves. The teacher can talk to everyone at once, like sending on MOSI, and listen for responses on MISO. But to talk to a specific student, the teacher calls their name. That name is the unique CS line. So the communication flow goes like this. Initially, the master keeps all the CS lines ICH inactive. All slaves are listening but ignoring MOSI and keeping their MISO output disabled in a high impedance or tri-state mode. When the master wants to talk to, say, slave #2, it pulls only the CS line connected to slave #2 low W. This wakes up slave #2. Now, any data sent on MOSI is meant for slave #2, and only slave #2 is allowed to put data onto the shared MISO line. All other slaves, slave #1, slave #3, etc., remain inactive because their CS lines are still HEH. The master communicates with slave #2. When finished, the master pulls slave #2's CS line back HEH. Slave #2 goes back to sleep and disables its MISO output. If the master then wants to talk to slave #1, it pulls slave #1 CS line LW, talks to it, and then pulls its CS line HEH again.
So it's like activating them one at a time using their dedicated enable line.
Precisely. So, if your microcontroller needs to talk to a flash chip, a display, and an ADC sensor using SPI, they'd all share the SCK, MOSI, and MISO pins. But you'd need 3 separate GPIO pins on your microcontroller dedicated to the CS lines for each of those 3 devices. A couple of tips for reliable multi-slave. Always make sure only one CS is low at any given time. Ensure slaves correctly tri-state their MISO line when deselected. This is vital to prevent bus contention, where multiple devices try to drive MISO simultaneously. Sometimes pull-ups on the CS lines add robustness, and definitely use software NSS mode on the microcontroller so you have full manual control over those CS pins.
Okay, that parallel CS approach for multiple slaves is clear.
Yeah.
But sometimes you hear about daisy chaining with SPI. How is that different? How does that work?
Daisy chaining. That's a totally different topology, usually for specific types of devices like shift registers or certain LED drivers. It's not the standard way you'd connect, say, a sensor and flash memory. In a daisy chain, the slaves are connected in series, one after the other, like links in a chain. The MISO output of the first device connects to the MOSI input of the second device. The MISO of the second connects to the MOSI of the third, and so on. The MOSI from the master goes only to the first device in the chain, and the MISO back to the master comes only from the last device in the chain.
Okay, data flows through the devices.
Exactly. And here's the other key difference. There's usually only one chip select line for the entire chain, shared by all the devices, along with the shared SCLK. The way data moves is like a bucket brigade, or shifting bits through a long register. The master sends, say, 3 bytes of data if there are 3 devices. The first byte goes into the first device. When the second byte is sent, the first device shifts its original contents out on its MISO, which is connected to the second device's MOSI, and takes in the second byte. This continues down the line. After the master has clocked out all 3 bytes, the first byte sent is sitting in the third device, the second byte in the second device, and the third byte in the first device. The data that comes back to the master on MISO is whatever was originally in the last device, having been shifted all the way through the chain.
Whoa, okay, so you shift data through all of them.
Yes. And then, when the master raises the single CS line HIGH, all devices in the chain typically latch the data that's currently sitting in their internal shift register simultaneously. This only works if the devices are specifically designed for daisy chaining. And notice, there's no individual addressing here. The position in the chain determines what data a device gets or processes. It's less common for general peripherals, but very useful for things like controlling long strings of individually addressable LEDs or expanding GPIO using shift registers.
Gotcha. Very different from the parallel CS method. Okay, one last question on the fundamentals. The bits themselves. How is bit order like MSB first versus LSB first handled in SPI, and why does that even matter?
That's a small detail that can cause big headaches if you get it wrong. Bit order simply defines the sequence in which the individual bits of a byte are sent over the wire. MSB first means the most significant bit, bit 7, an 8-bit byte, is transmitted first. LSB first means the least significant bit, bit 0 goes first. Why does it matter? Because the master setting must match what the slave device expects. If the master sends MSB first, but the slave expects LSB first, the byte received by the slave will be bit reversed. The data will be completely scrambled or misinterpreted.
So sending the 100,000,000 could look like 100,000,000 if they agree, but 100,000,000 if they disagree on the order.
Exactly. It leads to total data corruption. Thankfully, the vast majority of SPI peripherals, flash memory, sensors, displays, ADCs use MSB first as their standard convention. So that's usually the default setting you'll use on the master microcontroller as well. But you should always verify in the slave's datasheet, just in case, and configure your microcontroller's SPI peripheral accordingly. For example, setting SPI first bit MSB or SPI first bit LSB and STM32HHL. Getting this wrong is another one of those simple mistakes that can waste hours of debugging.
Right, always check the data sheet. Okay, we've covered the fundamentals really well. Now let's talk performance and reliability. What factors really impact how fast you can run SPI? And maybe more critically, what limits how long you can realistically make an SPI cable?
Good questions, moving into the practical physical limits. The main factor determining SPI speed is, of course, the clock frequency, SCLK, set by the master. This can range from maybe 1 MHz up to 50 MHz or even higher on capable microcontrollers, but you're always limited by the slowest device on the bus. You have to check the maximum SPI frequency specified in the datasheet for your peripheral chip. Running faster than the peripheral can handle will cause errors. The microcontroller's capability matters too. Can it actually generate and process data at that speed? Using DMA helps immensely here. The specific SPI mode, CPOL CPHA, can sometimes subtly affect the maximum reliable speed due to timing margins. Bus loading, having many slaves connected, especially sharing the MISO line, can increase capacitance and potentially introduce crosstalk, limiting top speed, and critically, PCB layout and signal integrity. Long traces, poor grounding, impedance, mismatches these cause reflections, ringing, and noise, which severely limit your maximum reliable clock speed. Good layout is essential for high-speed SPI. Oh, and voltage levels play a role. Lower voltage systems like 3.3V generally allow for faster signal transitions than 5V systems, potentially enabling higher speeds.
Okay, lots of factors for speed. What about cable length? Why can't I just run a long SPI cable across the room?
Yeah, that's a common wish, but SPI is really not designed for long distances. Several reasons why. First, it uses single-ended signaling, not differential pairs like Ethernet or RS-485. This makes it much more susceptible to picking up noise over longer wires. Second, those fast clock edges, even at moderate speeds like 8 MHz, can cause significant signal reflections and ringing on longer, unterminated cables due to impedance mismatches. This corrupts the data. It also radiates electromagnetic interference, EMI. Third, there's no built-in error correction. One noise spike flipping a single bit can corrupt an entire transaction, and the protocol itself won't notice. Fourth, the signals are unbalanced, which can lead to ground bounce and timing skew issues that get worse with cable length. So, the practical recommendations. For high speeds, say 10 megahertz, keep wires extremely short, ideally under 30 centimeters, maybe even just 10, 15 centimeters on a PCB. For lower speeds, maybe under 500 kilohertz, you might get away with 1 or 2 meters, especially if you use shielded or twisted pair cables and are careful about noise. Anything beyond 2 meters is really asking for trouble, unless you use special SPI bus buffer chips or convert the signals to something more robust like RS-485. Trying to run fast SPI over long wires is like trying to have a clear whispered conversation across a noisy stadium. The message just gets lost.
Okay, so keep it short, especially at high speeds. Good rule of thumb. Beyond the cable itself, what are the really crucial electrical and hardware design considerations to make SPI reliable in an embedded system, maybe specifically thinking about using an STM32?
Right. Getting the electrical details correct is paramount for reliability. First, voltage levels. We touched on this. Ensure the STM32 and all SPI slaves operate at the same voltage, commonly 3.3V. If not, use bidirectional level shifters. Don't connect a 5V peripheral directly to a 3.3V STM32 SPI pin or vice versa without proper level shifting. Second, signal integrity. Keep PCB traces for SCK, MOSI, MISO, and CS short and direct. Avoid routing them new noisy components like switching regulators. Use a solid ground plane underneath. Consider the small series termination resistors, 2233 ohms, on SCK MOSI placed near the STM32 master to dampen reflections, especially if traces are longer than a few centimeters or speeds are high. Third, decoupling capacitors, absolutely essential. Place a small ceramic cap, 0.1 UF or 0.01 UF, physically close to the VCC pin of every single chip on the SPI bus, master and slaves. Also add a larger bulk capacitor, 1 UF to 10 UF tantalum ceramic, somewhere nearby on the board's 3.3V rail. This provides clean, stable power during the fast current spikes of SPI communication. Fourth, pull-up, pull-down resistors. As mentioned, a 10K pull-up on each CS line to VCC is good practice to prevent unintended activation. Also, check data sheets for pins like HLD tag or WP tag on flash memory. They usually need pull-ups if unused. Don't leave inputs floating.
Okay, voltage, signal integrity, decoupling, pull-ups. What about routing the shared lines?
Good point. Hardware routing. MOSI, MISO, and SCK are shared. Route them as parallel tracks where possible, ideally with ground traces interleaved or on an adjacent layer. Try to keep their lengths roughly matched, especially SCK and MOSI, to minimize timing skew. Keep them away from high frequency or high current traces. And crucially, MISO contention. Ensure slaves properly tri-state, go high impedance, their MISO output when their CS line is high GH. If two slaves try to drive MISO at the same time because one didn't disable correctly, you get bus contention, which corrupts data and can even damage the pins. For longer off-board connections, if you absolutely must, using twisted pairs, for example, SCK twisted with GND, MOSI twisted with GND, or shielded cable, can help reject noise, but reducing speed is still often necessary.
And any specific tips for STM32 microcontrollers?
Yeah, a few STM32 specifics. Always try to use the dedicated SPI peripheral pins listed in the datasheet. They're optimized for speed and signal integrity compared to general GPIO pins. Choose software NSS mode for CS control when dealing with multiple slaves or needing precise manual control over the CS timing relative to data. Hardware NSS is usually only suitable for single slave setups. Definitely leverage DMA for any significant data transfers. Configuring SPI with DMA on STM32 using HAL or LL libraries drastically improves performance and frees the CPU. And be mindful of interrupt safety if you're controlling CS manually in an interrupt-driven system. Make sure CS toggling happens atomically, perhaps by disabling interrupts briefly, to prevent race conditions if another interrupt tries to use the SPI bus simultaneously.
That's a great list of practical hardware tips. You mentioned DMA again as a performance booster. Can you explain a bit more how DMA transfers actually work with SPI on a microcontroller? And how does it really compare speed-wise to just polling or using interrupts?
Sure, DMA, direct memory access, is like giving the SPI peripheral its own dedicated data mover that bypasses the main CPU. Here's the typical workflow for, say, receiving data using DMA. 1. Your CPU code configures the SPI peripheral, mode, speed, etc. 2. It configures a DMA channel to transfer data from the SPI peripheral's data register to a specific buffer in RAM. You tell the DMA how many bytes to transfer. 3. You manually pull the slave's CS line LOW4. You enable the emit channel in the SPI receive process. Critically, for receiving data, you often need to trigger SPI transmissions, sending dummy bytes, via DMA as well to generate the clock signals. So you might set up another DMA channel to send dummy bytes from a memory location to the SPI transmit register. 5. The DMA engine then automatically handles everything. As each byte arrives in the SPI receive register, the DMA controller grabs it and puts it into your RAM buffer without the CPU doing anything. Simultaneously, the other DMA channel might be feeding dummy bytes to the SPI transmit register. 6. Once the specified number of bytes has been transferred, the DMA controller triggers a single interrupt to the CPU, signaling transfer complete. 7. Your interrupt handler then knows the data is ready in the RAM buffer, and it pulls the CS line HHH.
So the CPU just sets it up and gets an interrupt when it's all done.
Exactly. The CPU is completely free during the actual byte-by-byte transfer to do other tasks. The same principle applies for transmitting data. DMA moves data from your RAM buffer to the SPI transmit register automatically.
Okay. The benefits seem clear. CPU offload, speed.
Huge benefits. CPU offered is the biggest one. The CPU isn't wasting cycles pulling flags or handling per-byte interrupts. This leads to high sustained speeds, often limited only by the SPI clock and peripheral capabilities. It ensures real-time responsiveness because the CPU isn't blocked, and it makes handling large buffers for things like display updates or flash reads-writes very efficient. It's practically essential for things like driving graphical displays smoothly or streaming audio data over SPI.
How does it compare to the other ways?
Let's quickly compare. Polling-based SPI. Simplest code, CPU loops, checks a flag, SP flag TXE to send, SP flag X and to receive. Reads, writes a byte, repeats. Pro, very easy. Con, CPU is 100% blocked during the transfer, terrible for performance and responsiveness. Only suitable for very short, infrequent transfers where blocking isn't an issue. Interrupt-based SPI, more efficient than polling. SPI peripheral triggers an interrupt when transmit buffer is empty or receive buffer is full. CPU ISR, interrupt service routine, reads, writes 1 byte, then returns. Pro, CPU can do other tasks between bytes. Con, still has ISR overhead for every single byte, can be complex to manage state machines within the ISR for longer transfers, good for moderate bursts of data. DMA-based SPI, most efficient. DMA engine handles entire blocks of data, CPU only involved in setup and completion interrupt. Pro, 0 CPU usage during transfer, highest possible throughput, predictable timing. Con, more complex initial setup configuring DMA channels, best for large, frequent, or high-speed transfers.
That's a great breakdown. DMA seems like the way to go for anything serious. Now, shipping back to reliability. Since SPI itself doesn't have error checking, how can you actually handle potential errors and build robust systems? What can go wrong, and how do you fix it or work around it?
That's the million-dollar question for robust SPI design. Because the protocol is so simple, errors often manifest as just garbage data or no response. Common errors we see include mismatched CPOL CPHA. We talked about this. Data is garbled. Fix. Check data sheets. Ensure master and slave match. Incorrect bit order. MSB LSB. Data appears bit reversed. Fix. Check data sheets. Configure master correctly. Faulty CS handling. Forgetting to pull CS low. Glitches. Pulling it high too early, especially with DMA. Fix. Careful GPIO control. Use pull-ups. Ensure CS stays low for the entire transaction. MISO line contention. Multiple slaves trying to drive MISO simultaneously. Fix. Ensure only one CS is active. Verify slaves tri-skate correctly. SPI interrupts DMA mismanagement. Race conditions. Incorrect setup. Buffer overflows. Fix. Careful configuration. Atomic operations. Proper buffer sizing. Clock rate too high. Exceeding master or slave capability. Fix. Reduce SCLK frequency. Long wires PCB trace issues. Noise, reflection, signal degradation. Fix. Short traces, good layout, lower speed, maybe termination resistors.
Okay, so preventing those is step one. But what if errors still happen? How do you detect and recover?
You need strategies at the application level, above the raw SPI transfer. 1. Add application level CRC or checksums. For important data, like configuration blocks or commands, calculate a checksum or CRC on the data packet before sending. The receiver calculates it on the received data and verifies it matches the transmitted checksum. If not, the data is corrupt. Request a retry. 2. Retry on timeout or invalid response. If you send a command and don't get the expected response, or any response, within a certain time, assume an error occurred and retry the command a few times before giving up. 3. Add status register checks. Many SPI devices have status registers, like the WIP bit in Flash. Reading these after operations can confirm success or indicate specific error conditions reported by the slave itself. 4. Use debug pins or logging. Toggling a GPIO pin before and after SPI transactions or logging key steps can be invaluable for debugging intermittent issues later using a logic analyzer or trace tool. It's about building layers of checks and recovery mechanisms on top of the basic SPI communication.
That makes sense. Add the intelligence in your application code. What if you have that tricky situation where the master and slave devices simply require different SPI modes, CPOL, CPHA? Is there any way to make them talk?
Right, that's a tough one. The short answer is, if the modes are fundamentally different, e.g., one needs mode 0, the other needs mode 1, they cannot reliably communicate on the same physical SPI bus wires. The timing will be wrong. The primary and usually only robust solution is check the slave datasheet first to confirm the required mode. Then configure the master to match. If you only have slaves that all use the same mode, you're fine.
But what if you genuinely have multiple slaves and they need different modes, like a mode 0 sensor and a mode 3 display?
In that specific scenario, you cannot connect them to the same SPI peripheral pins on your master microcontroller. The SPI peripheral on the micro can only be configured for one mode at a time. The solution here is to use separate SPI buses. Fortunately, most modern microcontrollers like STM32s have multiple independent SPI peripherals, SPI1, SPI2, SPI3, etc. You'd connect the mode 0 sensor to the pins for SPI1 and configure SPI1 for mode 0. Then you'd connect the mode 3 display to the completely separate pins for SPI2 and configure SPI2 for mode 3.
So dedicate a whole SPI peripheral block to each mode needed.
Exactly. It uses more pins, but it's the correct and reliable way to handle slaves with incompatible mode requirements. What you absolutely should not do is try to somehow fake it in software or hope it just works at low speeds. Mismatched modes fundamentally break the timing protocol. Don't waste time trying to force it. Use separate peripherals if needed.
Okay, clear advice there. Use separate buses. Final question. SPI is master-driven. The master initiates everything. So how does the master know when a slave device, maybe a sensor doing a measurement, has actually finished its task and has data ready to be read? The slave can't just interrupt the master over SPI, can it?
That's a very practical point. The slave can't initiate communication, so the master needs a way to figure out when the slave is ready. There are a few common methods. 1. Status register polling. This is probably the most common. The master periodically sends a specific read status command to the slave. The slave responds with a status byte, and the master checks a particular bit, like a data ready flag or an operation complete flag within that byte. When the bit indicates readiness, the master then initiates the actual data read command. Flash memory WIP polling is exactly this pattern.
They keep asking, are you ready yet?
Basically, yes. Method 2 is a fixed processing delay. The master just waits. It sends a command to start a measurement, then simply delays for a known amount of time based on the slave's datasheet specification for how long that operation should take. After the delay, it assumes the data is ready and reads it.
Seems simple, but maybe risky.
It is simple, but risky. If the slave's processing time isn't strictly deterministic, maybe it varies with temperature or workload, the master might read too early and get old or invalid data. It's only suitable if the timing is very well defined and consistent. Method 3 is much better if available. Use of a DRDY or IRQ pin outside SPI. Some sensors or peripherals provide an extra GPIO output pin, often called data ready, DRDY, or interrupt request, IRQ. The slave drives this pin, e.g. pulls it low or high, when it has finished its task and data is ready. The master can connect this pin to one of its own GPIO inputs, configured perhaps as an interrupt input. When the interrupt fires, the master knows the slave is ready and can then initiate the SPI read transaction. This is very efficient and interrupt-friendly.
So an external signal flag.
Exactly. A hardware handshake, essentially, but outside the SPI lines themselves. And fourth, sometimes you might see a more complex handshake protocol defined for a specific device, perhaps where the slave responds with a specific acknowledgement byte over MISO when ready, after being pulled by the master. Best practices. Use status register polling for simpler devices or things like flash memory busy checks. Definitely prefer using a DRDY RUQ pin if the slave provides one, especially for real-time sensors where you want event-driven reads. Always check the slave's datasheet. It will specify the expected timing and how it signals readiness.
This has been incredibly insightful, really getting into the nuts and bolts of SPI. We've covered what it is, how it stacks up against others, seen tons of practical uses like memory and displays, and really dug into the hardware details, the software flows, DMA, and error handling. Understanding SPI really does feel like unlocking a key part of embedded systems design.
It truly does. And maybe a final thought to leave you with. Knowing how these electrical pulses turn into data is one thing, but really grasping the details, the dance of CPOL and CPHA, the necessity of polling WIP, the strategies for multi-slave communication, the pitfalls of signal integrity, that deeper understanding is what allows you to effectively debug when things go wrong, to optimize performance, and honestly, to innovate in ways that just aren't possible if you only treat it as a black box. What surprising digital handshake might you uncover or design in your own projects now?
That's a great challenge. Hopefully this deep dive has given you the confidence to maybe explore that SPI sensor you've been curious about, or tackle that embedded project, knowing a bit more about the communication happening under the hood. Thanks for joining us on the deep dive.